Hello there. Time to get started on the problems of section 2. So I have the definition of E. I will start with that one. And we have the cusps here and the values of t. And we start with the cusp at infinity, or with infinity. So here we can just let z tend to I infinity. And since the sum converges absolutely, we have k larger than or equal to 5, then we can do it term-wise. So when m is distinct from 0, it tends to naught. So it's only the case where m is naught we need to worry about. And that only gives unity when n is 1. And that dates back to the group that we are summing over. That's the when m is naught, that comes from A, B, D here. And that means it has the form plus minus t to some power r. But the group we are summing over, we only take one representative of each of these, being n equals to 1 here. So that means when m is naught, we only have n equal to 1. And that means that the limit that's just 1. All right. Now, when we go on to the other cusp, I think we should just operate on this sum. So first let's do it all. Sum. And then we take the square root z to k halves. Or is it minus? My God, I forgot the definition here. I'll just look it up. I found it on page 186, so it should be minus. So let's believe that we can just multiply it inside here. So it's minus m plus nz. And then we take the limit. And that means if n is distinct from naught, which it is because it's positive, then it tends to naught. So each term tends to naught. Now there's an interesting thing. The value of t should actually mean something here, and I totally forgot about that. So I'll just make a break and then redo all this. I was right. This matrix It doesn't matter here when it's naught, but it will matter when we have the next cusp. So the matrix is this guy, and t is minus the imaginary unit. So we see some cancellation will occur here. Could we do something? If we take the square, then this will cancel. So if n is distinct from m, it will tend to now have been wrong all from the beginning. If it's set to minus k half, that will turn to naught. Oh, yeah, so if n is distinct from m, it'll turn to naught. So we only need to take into account the case where n equals m. But when they are equal, that's these guys. That can't happen. If 4 divides m and they are equal, then 4 divides both. So that means that it will always tend to naught. Well, that's my solution right now, that this will tend to naught. I have a bad feeling about it. So I'll just mark it as a question mark. I have to think a little more about it. And I guess I have to stop now. You see, I have a mason coming today, a bricklayer, and he's going to lay some, what's it called, tiles to the floor in my bathroom. And he has to cut them, and that will make a lot of noise. I believe I'm right, but I have a bad feeling about this result. So I'll just go through it again, and then we can do F. I just wanted to see if the noise was sufficiently low that I could continue with the second half of the problem. So I've written up not the definition, but the sum giving capital F k halves. We see what happens when z turns to infinity. That gives naught at all times, because n is positive. So that tends to naught. Then we take the cusp naught, and now we better do it correctly. I have a feeling this should not vanish, you see. S point, and I believe it was -1t, just check. T is -1. If we square, then this will tend to naught whenever m is distinct from 0. So that is, we only have the case m is 0 and n is 1 that we need to consider. Where this gives unity. Or does it? N was 1, so it's actually, oh, it's not epsilon k, it's the opposite way, it's epsilon n divided by k, to the power of k. And when n is 1, it gives unity, right? So this gives unity, and it was n equals 1, m equals 0. M we'll just check where all this lies. Oh. 4 divided by minus z, that lies in h. So the square root lies in the first quadrant. You know what, we'll just set k to 1 here. Now, this is an h, the square root is in first quadrant, so minus to minus first, that lies in the fourth quadrant. Minus z is below the real axis, so the square root is in first quadrant, so the reciprocal one is in the first quadrant, and this means that it has positive real part. And the square is 4, so that means it should tend to 2 to minus k halves. That's unity. Surprise. And let's see if we can do the last one as well. I'll just see I made the mistake already here. So it's minus, yeah, we have it here, 4zn. So it's 4n z divided by 2z plus 1 minus m times minus I times 2z plus 1 so minus k halves, and we reduce it for n minus 2m z minus m so we consider the square, then this will cancel and we only get this. So in the limit, all those where 2n minus m vanishes, tend to naught. No, all those where this parenthesis fails to vanish tends to naught. So it's only when it vanishes we get something non-zero. And what does it mean that it vanishes? It means that 2n equals m, and that implies that n is even because 4 divides m, but that means that the 2 divides both m and n. So there are none of these. So I claim that this sum gives naught as well, or tends to naught as well. This is quite weird. So all combinations of E and F should give naught at 1/2. But I think when k equals 5, what we have here is generated by f to the 5th and theta to the 4th f. Oh, how was that? I need to look that up. So we need to check that the value at 1/2 of all these guys generating the space vanishes. That'll give me a reality check to these results. that this was wrong. It's spanned by this and theta to the fifth. And theta is 0 at the cusp 1/2. That's why we inherit the zeros here. While editing, I realized that I hadn't addressed this question: verify the cusp conditions. And that's because when we have a finite limit, then the cusp conditions are fulfilled, that there are no negative powers of q occurring in the sum. But maybe we should recall the argument for that, because that's quite a while ago we made that. The point is to consider, I will just have a new one, the map let's take the limit here with imaginary value of z being larger than unity. That's an open part of H. And by this map, it is mapped to the open unit circle with naught excluded. And since the function, whatever it may be, is holomorphic, this map is as well. So to find the value in here, we just take any original point. I have no idea where that is. Let's say it's here. And then take the value of f at this point. And whichever we choose, it gives the same. At 0, we can either have that it's a removable singularity, in which case f is holomorphic, so we only have positive terms in the Q expansion. It could be a pole, in which case we have it will tend to infinity. The values will tend to infinity. The numerical value or the modular will tend to infinity. Or it can be an essential singularity, in which case all in any neighborhood of naught, all complex values will occur. And that means that when we have a limit, as we tend to I times infinity, then neither of these two last cases can occur. Therefore, it's sufficient to show that it has a limit, to show that it's a form, or that they all the limits are naught. No, yeah, to show that it's a cusp form.